Hello, my dear students. In the last class, I explained how stresses are developed in oblique section of a body when it is subjected to direct stress in one direction, and also subjected to two mutual perpendicular direction, and also direct stress accompanied by the shear stress. So today we will discuss stresses on an oblique section of a body subjected to direct stresses in two mutually perpendicular directions accompanied by a simple shear stress. Okay, so let us consider this rectangular body of uniform cross-sectional area and unit thickness subjected to tensile stresses along x axis and y axis accompanied by the positive clockwise shear stress along x axis as shown in the figure. See here you can see this is the direct stresses acting in both the direction, x direction sigma x and y direction sigma y. Right. In addition to that, there is a shear stress along x axis as well as y axis. See here sigma xy, and this is also sigma xy. Now let us consider an oblique section AB inclined with XX axis on which we are required to find out the stresses as shown in the figure. Okay, here you can see here this is tau xy and this is also tau xy. This is, see here you can see tau xy this direction, and this is you can see here this direction. Okay, see here one thing you have to remember, this is tensile force, so plus. Okay, sigma x is positive. If it is compressive force, then you have to take it as minus. And similarly, if the stress is moving in this direction along this direction, then you have to say this is positive. Okay, if the stress is acting in this direction, okay, then you can consider it as a negative force. Okay, then we will see, let us same how we have derived in last cases, same thing here. Let sigma x is tensile stress along x axis and sigma y is tensile stress along y axis, and tau xy is positive, that is clockwise shear stress along x axis. Then theta is angle which the oblique section AB makes with x axis in an anti-clockwise direction. Okay, let us consider the equilibrium of the wedge ABC, that is this one A, B, C, ABC. Okay, then we know that as per the principle of simple shear, the face BC of the wedge will be subjected to an anti-clockwise shear stress equal to tau xy. Okay, now we know horizontal force acting on the face AC, P1 is equal to sigma x into AC, and P2, that is vertical force, that is equal to tau xy into AC, and vertical force acting on the face BC, that is sigma y into BC, and horizontal force on the face BC, P4 is equal to tau xy into BC. Okay, after that you have to derive this. You will have this equation, then you have to substitute all these values here, then you will get the final normal stress, that is equal to sigma n, that is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 into cos 2 theta minus tau xy sin 2 theta. Okay, this you remember, this final formula. Okay, see this you remember, tau n is equal to this. Okay, next we'll see how to find shear stress or tangential stress across the section AB. Okay, again you have to derive this. I don't want to explain this, it is not required also. Okay, so just remember this final, what is tau. Tau is equal to sigma x minus sigma y divided by 2 into sin 2 theta minus tau xy into cos 2 theta. Okay, Okay, this is the shear stress or tangential stress across the inclined section AB. Next, here also we have maximum principal stress and minimum principal stress. Maximum principal stress is given by this formula. Sigma P1 is equal to sigma x plus sigma y divided by 2 plus square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. Okay, similarly minimum principal stress is given by this equation that is tau sigma P2 is equal to sigma x plus sigma y divided by 2 minus square root of sigma x minus sigma y divided by 2 whole square. Okay, plus tau square xy. This formula final, this equation you remember. Then let us see one example. A point is subjected to a tensile stress of 250 MPa in the horizontal direction and other tensile stress of 100 MPa in the vertical direction. Okay, the point is also subjected to a simple shear stress of 25 MPa such that when it is associated with the major tensile stress, it tends to rotate the element in the clockwise direction. What is the magnitude of the normal and shear stresses on a section inclined at an angle of 20 degree with the major tensile stress? This is the given example. So what is the what here it's given? Tensile stress in horizontal xx direction, that is nothing but sigma x, that is equal to 250 MPa. Next, tensile stress in vertical yy direction, in the vertical direction. See here, tensile stress in the horizontal direction is nothing but xx. Okay, and tensile stress in the vertical direction, that is nothing but yy. Okay, so tensile stress in vertical y direction, sigma y is equal to 100 MPa. Next, the point is subjected to simple shear stress of 25 MPa, that is tau xy is equal to 25, such that when it is associated with major tensile stress, it tends to rotate the element in the clockwise direction. That's why it is plus 25 MPa. And angle made by the major tensile stress is 20 degrees. So direct substitution, you have that formula. What is that? Normal stress is equal to sigma n is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 into cos 2 theta minus tau xy sin theta 2 theta. So substitute all the values, you know, simplify this, you get sigma n is equal to this 101.48 MPa. Okay, then you have to find this shear stress. What is shear stress? Shear stress is given by this formula. Tau is equal to sigma x minus sigma y divided by 2 into sin 2 theta minus tau xy cos 2 theta. Okay, substitute here, sigma x is 250, sigma y is 100, theta is 20 degree. So simplify this, you get tau is equal to 29.06. Very simple, direct substitution. Only you have to remember the formula. That's it. Okay, let us take one more example. A plane element is subjected to tensile stress of 400 MPa on one plane and 150 MPa on the other at right angles to it. Each of the above stresses is accompanied by a shear stress of 100 MPa such that when associated with a minor tensile stress tends to rotate the element in anti-clockwise direction. Find principal stresses and their directions. Second case, maximum shearing stresses and the directions of the plane on which they act. Okay, so what is given here? Tensile stress along x-axis, that is 400 MPa. It is in one plane. Okay, so you just consider here, this is first one you consider as x direction, sigma x, and second plane which is on the other at right angles to it, that is sigma y. Sigma x is equal to 400 MPa and sigma y is equal to 150 MPa. then shear stress is equal to 100, but I have considered here minus because this element tends to rotate the element in anti-clockwise direction, so it is minus. So minus sign due to anti-clockwise on xx direction. So direct formula, you have principal stresses. What is that formula? Maximum principal stress is given by this equation, sigma x plus sigma y divided by 2 plus square root of sigma x minus sigma y divided by 2 whole square plus tau square xy. So substitute and simplify, you get maximum principal stress or tau sigma maximum is equal to 435.1 MPa. Next, what you have to calculate? You have to calculate my inner principal stress or minimum principal stress, that is given by this equation. What is that? Sigma minimum is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 whole square plus tau square xy. Substitute, you get minimum principal stress is equal to 114.9. After that, it is asked to find the magnitude and the direction of the principal stress. What you have to calculate? You have to calculate theta. How you get theta? You have one formula, tan 2 theta p is equal to 2 times of tau xy in divided by sigma x minus sigma y. 2 into tau xy is 100 divided by 400 minus 150 is equal to, you get 0.8, or 2 theta p is equal to 38.66. Simplify this, theta you get 19.33, or suppose okay, then you have to find what is maximum shearing stress and the direction. This is the formula is given here. Substitute all values you know, so you get this answer. Okay, and then you have to again here also calculate theta s, that is given by this equation, tan 2 theta is equal to sigma x minus sigma y divided by 2 times of tau xy. Substitute, you get 2 theta s is equal to 34 degree, or theta s is equal to 25.67 degree, 67 degree. So like this you can calculate what is the magnitude and stresses, normal stress, shear stresses. Okay, let us take one more example. You just go through this, you have to do, I don't do this. Finally, if you have any difficulties, we will discuss in the class. Okay, so a plane element of a body is subjected to a compressive stress of 300 MPa in x direction and a tensile stress of 200 MPa in the y direction. Each of the above stress is subjected to a shear stress of 100 MPa such that when it is associated with the compressive stress, it tends to rotate the element in an anticlockwise direction. The normal and shear stresses on the plane inclined at an angle of 30 degree with the axis. Okay, so what is given here? Sigma x is given, but this is compressive stress, so you have to take it as minus 300 MPa, and also tensile stress of 200 MPa, that is sigma y is equal to 200 plus, and shear stress, that is anticlockwise associated with the compressive stress, so it is, you have to take it as minus 100 MPa, and also it is given here, this is anticlockwise direction, so that is minus sign due to anticlockwise direction along the compressive stress, and angle is theta is 30 degrees. So direct substitution, use the formula and find the answer, and again for this also shear stress, use the direct substitution, find the answer. Okay, next class we will discuss if you have any difficulties in this chapter. Okay, I hope all of you understood. Thank you.